Assalamu alaikum. Our subject today is the workforce size model. For most of the companies, the workforce size vary from time to time, depending on the project needs. In a particular period, the company may need a specific number of workers. However, on the other periods or in the following period, this need may increase or decrease, depending on the need of the project. From period to period, they have to come up with hiring and firing strategies to maintain and satisfy their demand. Different scenarios can be used, as we know that hiring and firing costs the company amount of money. So the optimal scenario is the one with minimum cost. One of the easiest methods to solve this model is the dynamic programming. Let's assume that the plan will be executed over n weeks and that the minimum labor force required in week I is BI workers. Theoretically, we can use hiring and firing to keep the number of workers in week I exactly equal to BI. However, it may be more economical to maintain a labor force larger than the minimum requirement through new hiring, and this is the case we will consider. Given that Xi is the actual number of laborers employed in week I, two costs can be incurred in week I. C1 times Xi minus Bi, the cost of maintaining an excess labor force, Xi minus Bi, and C2 times Xi minus 1, the cost of hiring additional laborers. Xi minus 1, it's assumed that no additional cost is incurred when employment is disconnected. Now we will define the elements of the DP models. First, the stage which represents the periods in the workforce size model. Second, the state which represents the number of workers of the previous stage, I minus 1. Third, the alternatives at stage I, which represents the number of workers at period I. So the DP backward recursive equation is shown below. As you can see, the equation for the minimizing the cost, C1, C2, and the cost of previous stage, and it appears that Xi is greater than or equal to Bi, which means we have to satisfy the demand. As the backward equation is stated from the last period, which is the first stage, stage n, and we are going to terminate at stage 1. Example. A construction contractor estimates that the size of the workforce needed over the next 5 weeks to be 5, 7, 8, 4, and 6 workers, respectively. Excess labor kept on the force will cost $300 per worker per week, and new hiring in any week will incur in fixed cost of $400 plus $200 per worker per week. As we can see, n equal 5, which is the periods, number of periods. Bi, the minimum number required for month 1 is 5, month 2 is 7, month 3 is 8, month 4 is 4, and month 5 is 6. The 300 times Xi minus Bi is the cost of keeping used workers, and 400 plus 200 times Xi minus 1 is the cost of hiring additional workers. We start the solution from the last stages back to the first stage. Stage 5. So, as you can see, this is the formal table for solving this model. This is the equation for stage 5. The first column represents the state, which is the number of workers required from the previous week of its given, and it's given that the minimum number of workers required in week 4 equal 4 workers. We calculate that we cannot have less than 4 workers, and we cannot exceed more than 6 workers because it's the last period. And then we substitute x4 and x5 of the costs directly in the equation to find their total cost, which is represented in the second column. As we can see, the cost in state 4 is 8, of the number of workers is 6, and the optimal solution is 8, which correspond to x5 equal to 6. In stage 5, the cost is equal to 6, and the number of workers is also 6 workers, and the optimal solution is 6, which corresponds to x5 equal to 6. In stage 6, the cost is equal to 0 because we don't hire and we don't have any used workers. So the optimal solution is 0, which corresponds to x5 equal to 6. Stage 4. Next stage is stage 4. In this stage, the required number of workers is 4, which is represented by B4 equal 4. In filling the table, we can see that we only have one state, which is 8, and it's the required number of workers in week 3. We cannot have less than this, and we cannot have more, since 8 is enough to cover the following periods. From the previous stage, the alternative of x4 can be either 4 or 5 or 6. By substituting in the formula by x4 equal 4, x4 equal 5, and x4 equal 6, we see that the optimal solution is 6, which corresponds to x4 equal 6. Stage 3. By following the same steps we applied in stage 5 and stage 4, we can solve the remaining stages. When the state is equal to 7, the optimal solution is 12, and the number of workers are equal to 8. And when the state is equal to 8, the optimal solution is 6, and the number of workers are also equal to 8. Stage 2. For stage 2, the same procedure will be followed. At stage 5, the optimal solution is equal to 19, which corresponds to x2 equal to 8. And the number of workers are equal to 8, and so on for the cost for the rest of the stages. Stage 1. For stage 1, we will follow the same steps, so the results shown that the optimum solution is 33, which corresponds to x1 equal to 5. Now, we can find the optimum number of workers by starting from stage 1. From stage 1, the optimal number of workers in week I in week 1 is equal to 5. In stage 2, when x1 equal 5, the optimal number of workers in week 2 is equal to 8. In stage 3, when x2 equal 8, the optimal number of workers in week 3 is also equal to 8. In stage 4, when x3 equal 8, the optimal number of workers in week 4 is equal to 6. In stage 5, when x4 equals 6, the optimal number of workers in week 5 is equal to 6. Finally, to find the total cost, we construct this table and calculate the cost of hiring or firing workers for each week, and then we sum all the costs to find the total cost, which is here $3,300. Thank you for listening.